All right, we'll give it another minute or two and see if a couple more people can get on. Well, big difference in the weather in the last couple of days. We had 90s last week and then 30, 36, 37 yesterday. All right, well, those that come. So just going to start talking about a couple of things right quick. And what we're going to go over today is we're going to finish up. There's 5 or 6 slides left in chapter 17. We're going to finish those up right quick. We're going to start talking about the end of chapter problems and go through those for chapter 17 as well. That'll be the bulk of what we do with our time. And then, if y'all have any questions on any of the mastering chemistry problems or old test problems, we can do that as well. We can, I guess I need some input from, would y'all rather ask test questions today? Or would y'all rather come back tomorrow and ask test questions during our class period? So
tomorrow would be better, just so we be kind of like in a routine, just to do it at our normal time. And if we have any questions, we can just ask them or have them pre-planned. That way you can just go through it like normal.
All right, let me see if my volume's been turned down. I couldn't hardly hear you, Aaron. Okay, repeat that, please.
I think Wednesday would be good, just so we could do the same thing like we usually do. I think it would fit kind of like how we do it, so it'd be sort of normal.
Okay, I'm fine with that. So, so what we'll do then is we'll go through the end of chapter problems, and then if you want to ask some questions today dealing with the mastering chemistry, you can. But we'll save the test questions. I'll log in tomorrow. So I think I've got some standing. Let's see if I'm looking for my sheet that I've got all my office hours written down. Too many sheets piled up. Okay, so yeah, Wednesday I've got office hours set up for 11:30 to 12:30. So anybody wants to log in then, just log in and we'll go over exam questions tomorrow. So that's fine with me if we do it like that. So, all right. So just to make sure you've looked at the study guide, I hope you have. So I posted the study guide of things to look at. The test will be available Thursday and Friday. Just to let you understand how the format of the test is going to work. The exam is a little different from the homework in that you get one attempt to work each one of the questions. It's not unlimited attempts. You get one question at a time, and every one of you will have the questions in a different order. The questions will be either multiple choice questions or they will be the fill in the blank question. So what's called free form or free response in Blackboard. If you have something that's an equation that you need to solve, I think it's probably easier if you just if you write it down on a piece of paper, take a picture of it and upload that picture, email it to yourself and upload that picture. If you want to try to mess with the equation editor and put stuff in, you can. But if you want to get partial credit for solving a problem, you got to give me something to show me how you're doing it. I don't care that the format of the equation, as long as you can show what you're doing. If you want to type something out, that's fine. You don't have to worry about trying to get everything to look perfect with an equation editor. You got to show me that you the path that you're using to come up with a solution if you want partial credit on something. So, all right, does anybody have questions about the test before I go ahead and start with the materials we have for today?
Yeah, are we uploading pictures to the test itself, or is there going to be like an area?
No, so when you submit an answer to something, you can click on if it's a free response one, you can click on a picture there to add a picture to it. So you can't do that on the multiple choice, but you can absolutely do that to the ones that are free response. Okay. What else? All right. So with that, I'm going to share screens and go over and finish up the couple of slides we have in chapter 17, and then we'll go into the materials for the end of chapter problems. All right. Can y'all see chapter 17? Are the notes now? I think you can. Okay, so last thing we're talking about is how to calculate solubility. And we did a couple of example problems were the last thing that I went over on the video I posted for Monday. The next thing we want to talk about with this is something called the influence that ions that are not part of the solid have an influence on that solubility. And the term for this is called the common ion effect. And the common ion effect is an application of Le Chartier's principle, or the mass balance effect. So what happens is we have a salt that's slightly soluble, and if one of the participants in that solubility equilibrium, like something like calcium fluoride, dissociates into the calcium and the two fluoride ions. If somewhere there's another source of either one of these species, okay, so if we either have fluoride or if we have calcium from another source, something else that's soluble, what happens is that increases the concentration of that species, and it has an influence on the solubility equilibrium. For example, if we added some sodium fluoride is a freely soluble salt. What would happen is that if I added the sodium fluoride to this equilibrium, so let's throw some sodium fluoride in there. So sodium fluoride being a soluble substance would disassociate as a strong electrolyte to the sodium cation and the fluoride anion. So what that does is it increases the concentration of this fluoride, because the equilibrium doesn't know where the fluoride atom came from. It just knows there's fluoride present. So if we increase the concentration of a product, if you remember Le Chartier's principle, means it's going to drive this equilibrium back to the left, which makes it more insoluble. So the net effect is that it would decrease the solubility and push it back to the left. And that's true whenever we have something that's a slightly soluble substance, and if either of the species is added. The result of the addition of that common ion that comes from a secondary source decreases the solubility to a value lower of what it would have been if it was just dissolved in pure water. Well, how much lower? Let's look at an example of that. So on this example, this is looking at the molar solubility of silver bromide in pure water versus we'll look at it in 0.001 molar sodium bromide. So let's look at it with pure water first. And I'm going to show you a slightly different way to maybe calculate these or present these to set them up. So if you think about this, I'm going to write this equilibrium out again down here below. So silver bromide solid dissociates into the silver cation and the bromide anion. So if we think about the KSP expression, so I've got KSP. KSP would be products over reactants, so it would be the concentration of the silver cation times the concentration of the bromide ion. So if we think about what the solubility is the amount of the substance that goes into solution. So we call S, small s, the solubility. It's the amount of the silver bromide that dissolves, and it's the molar amount of it. So if we look at the stoichiometric ratio between the silver bromide and the silver cation, it's 1 to 1. So this would also be S, and this would be S. So if we look at now just substituting those S's in, so it would be S for the silver and S for the bromide. So KSP is just simply equal to S squared. That's where this term comes from. So if I want to find out what is the solubility, solubility is simply equal to the square root of KSP. And that's where the values come from in those tables. So if you remember the tables, I told you if it's a 1 to 1 salt, it's a square root of KSP. If it's a 1 to 2 salt, it's the cube root of KSP divided by 4. Well, that's a simple way to set this up and find out what these values are. And we'll do some that are all the possibilities as we go forward. So if you don't have the tables available, you can set these up and solve for what those values are for the tables to find out what the solubility is equal to fairly simply. So we know the value of KSP. I can look up that value of KSP in a table, and KSP is 7.7 times 10 to the minus 13th, and the solubility is just simply the square root of that. So I take the square root of it, it comes up to 8.8 times 10 to the minus 7th. Now that's the solubility in pure water. But now if I do that solubility in a presence of 1,000th molar sodium bromide. So sodium bromide is a freely soluble salt. So what that means is it's going to dissolve readily in a system. So if I put this 1,000th molar sodium bromide in, it dissolved. I've essentially just added 1,000th molar bromide to the solution. So when we look at the solubility of this system, the solubility is going to be thinking about what my the terms that we had, like we put on it a while ago. So the amount of the silver bromide that dissolves is S. The concentration of the silver would be S. The concentration of the bromide would be the solubility plus the 1,000th molar that came from the external source of the bromide. But when we look at this 1,000th plus the solubility, we said a while ago that the solubility in just pure water is 10 to the minus 7th. So we're adding something that's 10 to the minus 7th or smaller. The fact that we know we're adding a common ion is going to even reduce the solubility. So it's going to be less than something to 10 to the minus 7th. So what essentially this means is this solubility is insignificant compared to the size of the common ion that we've added. So if I get my pen to quit doing that. All right, so we just simply drop that out of the system, and it simplifies to the concentration of the bromide is the concentration that we added from this common ion. It's the 1,000th molar. So now when we solve the KSP expression, KSP is equal to the concentration of the silver, which is S, times the concentration of the bromide, which is 0.001. So if I want to solve for solubility, solubility is just equal to the KSP divided by the concentration of the bromide ion. So when I take and divide that, it's the 7.7 times 10 to the minus 13th divided by 1 times 10 to the minus 3. And it comes up to solubility is 7.7 times 10 to the minus 10th. So just adding this very dilute solution in here, so 1,000th molar, decrease the solubility of the salt by 3 orders of magnitude. So that's what the common ion effect does, is that a small amount of a common ion decreases the solubility of a slightly soluble salt. Now, another thing that plays a role on solubility is sometimes pH. So if the substance that dissolves produces an anion or a cation that is influenced by pH, what happens is that things like hydroxides, they're more insoluble at higher pH, and the solubility will increase when you go to lower pHs in solution. So the lower the pH of a hydroxide, the more the solubility. And the why of that is it relates back to the common ion effect. The higher the pH is in something, that means the higher the hydroxide ion concentration would be. So if we look at the pH going up, so let me get a pen I can write with. If I increase the pH in the system, think of a relationship with that. That means that it decreases the hydrogen ion concentration, because I have a higher pH. But the converse of that is it increases the OH minus concentration. As the OH minus concentration gets higher, mass balance effect is that this is going to shift back to the left. Now, the opposite of this is also true. If I were to take and reduce pH, so if I were to reduce pH in a system, if I reduce pH, that would mean that it increases the H plus concentration, and therefore it decreases the OH minus concentration. And if it goes down, the OH minus goes down, that's going to cause the equilibrium to shift in the forward direction. So if I have something like magnesium hydroxide, it's not soluble in water unless I take the pH down below to acidic pH. If you have the pH anything above 8 or so, the presence of the hydroxide will cause that to precipitate out even a higher level. But if I want to make it more soluble, I can cause the hydroxide concentration to decrease by putting it in an acid. So a common place that we see things like this are if we want to clean the residue off of a fixture. So like your sink fixture, it gets some calcium carbonate built up on it. So from water hardness, one of the main ways that we see the things from water hardness is we see the deposits of calcium carbonate. And if I want to clean that fixture up, what I can do is just take and put that fixture in some vinegar and let it sit there for 30 minutes and come back and it will have completely dissolved. Now the why of that is because of what happens because of the low pH of the vinegar. So the calcium carbonate dissociates to produce the calcium cation and the carbonate anion. But carbonate is a conjugate base. So if I take, and it's going to be influenced by the presence of an acid, so if I add H plus to it, this conjugate base is converted to the bicarbonate. So that means its concentration would decrease. So as this concentration would decrease, it increases the solubility of the calcium carbonate. So that's the common way that if you want to clean the calcium carbonate residue or the water spots off of glass, you put a little bit of vinegar on it. Okay. Same if you want to get the stuff off of your shower, the fixtures on your sinks and your faucets, you use a little bit of vinegar to clean those up. But anything where it has a the anion is a conjugate of a weak acid, it's always going to be more soluble at lower pH than at that higher pH. So the lower the pH in the system, the higher the solubility, just like it was with the magnesium hydroxide system above. If you look at the old test, I'll probably give you a test question like that. I'll give you a system, and I want you to either choose the one that solubility changes with pH, or I'll ask the opposite, which one does solubility not change with pH? That's a common type of test question that I want you to be able to know. All right, so we think about these last few slides. We're talking a little bit about precipitation and how, oops, that got small on me. When precipitation occurs, how will we know whether to predict whether it occur or not? And we talked about solubility in the solutions chapter a little bit. When we think about these ionic compounds, what we can do is we can compare the reaction quotient. So we talked about how to calculate these Qs when we were talking about would an equilibrium go in the forward or reverse direction. Now we're going to do the same thing, except the Q we're comparing is to the KSP that solubility equilibrium constant. So if the value of Q is equal to KSP, the system is at saturation and no precipitation forms. If Q is less than KSP, it means the solution is unsaturated and it still won't form a precipitate. And if Q is greater than KSP, this means that it is above saturation, and a salt that's above saturation should form a precipitate. Now, I should say should. We talked about how you could heat a solution to increase the solubility and then cool it down. You could create a solution that was a supersaturated solution, and typically a supersaturated solution won't precipitate until it's disturbed. But when you do disturb it, you'll find that you get an instant precipitation. So an example of this is silver, and you're adding into it, this is silver nitrate, which is soluble, and sodium chromate, which is soluble. So the chromate has a yellow color to it. But the moment those two things hit, as we drop the solution in, it forms the silver chromate. And if it meets the conditions where Q is greater than KSP, then it's instantly going to form a precipitate in the solution. Now, we talked about the example of the sodium acetate. Sodium acetate is a common one that we will heat up and it forms a supersaturated solution. But if we drop that one seed crystal in to disturb it, as soon as it drops down and hits the solution, it instantly snows out and makes this, forms this large crystal of the sodium acetate in the solution. Now, one of the other things that we do with precipitation is we form qualitative analysis. So qualitative analysis is when we do a selective precipitation to try to identify the presence of particular ions in solution. This is a classical wet chemistry technique that we do. We did something like this when we tried to identify a halide earlier in the semester. Let's see, that was last semester. We did a halide analysis. So we were trying to figure out which one of the halogens we added. We added a variety of different things to it to see if it formed a precipitate or not. Now, if we understand the solubility rules well, we can maybe do some of this by not doing comparisons to everything else. If we have multiple ions in a solution, we can do a series of tests and we can find out even if we have a mixture. But to do these tests, we need some precipitating reagents, and we need to understand that each reagent causes a specific ion to cause a precipitate, and then we can selectively rule out what's in a mixture. So this is just a quick example, and I'm not going to ask you to, in the rules or in the textbook, there are the solubility rules, and it gives you some examples of doing those. That takes a lot of memorization to get those down good, and I'm not going to ask you to do that. We talked about the soluble things in the solubility or in the solutions chapter. But let's say you had a mixture of 3 cations, cation A, B, and C, and you added the first reagent to it that would selectively precipitate cation A. So if cation A forms a precipitate and falls out of solution, you know that A was present. So each step we're looking for one thing in the system. So we're trying to figure out, is there A present in the first step? So then you would pour the liquid off the top. That's called decanting. And now you have cations B and C left. Now we add a second precipitating agent. And this time it's looking for cation B. So if it forms a precipitate with cation B, which is the black one, it would form the solid there. If not, I'd pour that off and I would have cation A. So we would have, the one that's left is cation C. We've already got rid of A. So the slide's mislabeled. If we have cation C left, we could assume that it's got to be cation C, but really if I want to be sure with that, I need to form a precipitate with cation C. So you need a test for it. You don't need to just make an assumption, but you need to test, is this C? If you know there's only a possibility of 3 things, you can do process of elimination, but it's better to have a confirmation in the system. Okay, so that's the material that that I want to cover, or that finish up the slides for chapter 17. Let me let this save. I want to go through and work the end of chapter problems, and I encourage you to ask questions as you need to on this. So if I'm going too fast on these things, you tell me to slow down or ask the question that you need. Okay, so the first question I have is question number 28. And question 28 says, a formic acid solution has a pH of 3.25. Which one of these solutions would raise the pH upon addition? So I've got to think about what this substance is and what's going to happen. So what type of acid is formic acid? Is it a weak acid or strong acid?
Weak acid.
It's a weak acid. Very good. So formic acid is a weak acid. So WA means weak acid. And what I want to know is which one of the solutions is going to increase the pH. So I want pH to go up in the system. So I want to do something that's going to take that weak acid and convert it into a more deprotonated state. Okay, so I want to raise the pH. So if I look at the things that I could add, so what kind of acid, if I add HCl, what is HCl?
A strong acid.
Okay, it's a strong acid, and strong acids dissociate 100%. So if it's 100% dissociated, what happens if I add this strong acid to a mixture of a weak acid is it's going to cause a decrease in pH. So it's going to go down. All right, so that's not what I want to accomplish, so it's not A. All right, if I add the substance that's in B, which is sodium bromide fully dissociates into the sodium cation and the bromide anion. Now, if we think about, is this an acid or a base? I need to add something that's going to have some base properties to raise pH. These are both conjugates to strong acid and a strong base. So this is what we classify as a neutral salt. So neutral salts don't have an influence on pH. And the same is true of KCl. So KCl is also a neutral salt, so much like what we had in B. Now, if I look at what we have in C, C is sodium formate, so it would dissociate into the sodium cation and plus the formate anion. And formate is the conjugate base to formic acid. Which is HCH2, HO2. Right, so what happens when I add this conjugate base to it? The conjugate base would absorb some of the proton, it would convert it, but it would cause the pH to increase. So adding the conjugate base is the one that would yield an increase in pH in it. So this type of question is just demonstrating that you have a good mastery of understanding acid-base chemistry. So something like a question like this is subject to a type of question you might see. All right, question number 40 says use the H&H equation to calculate the pH of each solution. And the H&H equation, or the Henderson-Hagenbach, we also call the buffer equation. So the buffer equation. And just a reminder of what that was, it said that pH is equal to pKa plus the log of the concentration of the deprotonated form divided by the more protonated form. Right, H&H equation. So A says calculate the pH of a solution that is 0.145 molar propionic acid and 0.115 molar potassium propionate. So to be able to do this, first thing I need to know is what is this pKa value? All right, so I need to know what is pKa. So if I know what the Ka is, pKa is equal to a negative log of Ka. So I just need to take my calculator and put in the negative log of that number. So I've got 1.3 times 10 to the minus fifth. And then need to plug that in. So 1.3 times 10 to the minus fifth. Take the log of it, and I get pKa is 4.89. When I round it to 2 decimal places, that's equivalent to 2 significant figures. Okay, so now I know that portion of it. I can go look at doing A. So pH is equal to pKa, which is 4.89, plus the log of the concentration of the deprotonated. So that would be the propionate, the potassium propionate. So that concentration would go on top. And what would go on bottom is the concentration of the acid form, the propionic acid. So now it's just a math problem. All right, so when I take this ratio, I get the ratio is 0.793. When I take the log of it, I find the log is a minus 0.1. So when I add that to the Ka, or the pKa, I see it's just going to go down by the 1/10. So the pH is 4.79 for solution A. All right, so all of these work a similar way. I'll go ahead and we can take a look at the next one and just let you understand how to do it, but they all are examples of doing buffers. So let's look at how we would do B as well. So B is a solution that is a percent by mass of C5 H5N. So if we think about what is that particular substance, we maybe have to go over here to our table and see if we got pyridine in our table. Is it at the bottom? Yeah, it's well, this is a base called pyridine. Maybe if we look at it and see if we got it under our acids. Yep. So here's pyridine. So this is the base that we have, and this is the Kb for it. So we'll Kb is 1.7 times 10 to the minus 1.7 times 10 to the minus 9. All right, so Kb is equal to 1.7 times 10 to the minus 9. Now the H and H equation tells us we need to know what the Ka is. So we need to find pKa. So we can use that Ka is equal to Kw divided by Kb. And if we take Kw, which is 1 times 10 to the minus 14th, and we divide it by the Kb we just found, 1.7 times 10 to the minus 9th, we can find out what Ka is. And Ka is 5.9 times 10 to the minus 6th. And if I do the same thing, take the negative log of that, I find that the pKa is 5.23. Okay, 5.23. Okay, so now I know what the Ka portion of it is. So the next step would be to take these percent by mass concentrations and convert those into molarity. Now to do that, I need to know what the density of the solution is. I'm going to assume that the density is 1. So if I start with the first form, which is the base form of it, so the base form would be the deprotonated. So it's 0.785 percent by mass. So it'd be grams of C5H5N per 100 grams of solution. All right, so 100 grams of solution. And I'm going to assume the density of the solution is 1. So 1 gram per milliliter times 1,000 milliliters per liter. So now I need to know what is the molar mass of this. So if I look at C5 is 60 plus 5 plus nitrogen is 14. It weighs about 79 grams per mole. So 79 grams of C5H5N per 1 mole of C5H5N. So now when I multiply that out, grams would cancel out of that material, grams of solution would cancel out, milliliters would cancel out, gives me moles per liter. So if I just want to find out what it is, I find that it's right at 0.1 molar. 0.0994 molar C5H5N. Now I'm going to do a similar calculation, except now I'm going to have to use this compound. So I'm going to have to figure out what its molar mass is. So it's got this many grams of C5H5N HCl divided by 100 grams of solution. And I'm going to do the same conversions. So I'm going to assume that the density is 1. I'm going to convert from milliliters to liters. And now it's the molar mass, which was 75, but this has an extra HCl on it. So add 1 for the H, and Cl is 35.5. That means it weighs 115.5 grams per mole. C5H5N HCl per mole. And that'll give me the molarity of that species. So 0.85. And this one's slightly less dilute. Oops, I think I got a typo. I either did something wrong in this one or I did something wrong in the first one. Better, okay. Yeah, I had one too many zeros in there. Okay, so now I know the molarity of this one. So the last thing I need to do is calculate what is the pH. So pH is equal to pKa. We said the pKa was 5.23. And then it would be the log of the form that's deprotonated, that has the fewest number of protons, is the base form. So that would go on top. The protonated form would go on the bottom. So you just take the ratio, divide it, get the log of it, and then add that to the pKa. So the ratio is 1.166. So I take the log of that, and the log of this comes up to be 0.07. And if I add that, I can actually do that without a calculator. pH is going to be 5.3. So if we just think about the difference between those two problems and the strategies we have to use to solve them, they both use the buffer equation. That worked the same on them. The difference was the first one we had the molar concentrations, could plug it directly into it. The second one was more difficult in that the information we had to use to get the Ka was a little bit more difficult. We had to calculate from Kb, then go to pKa, and then the concentrations weren't given to us in molarity. We had to go from this percent by mass, converted into the molarity, but the way we solved it was exactly the same. Same type of problem, just a little bit more difficult version of it. So any question on either of those? I can absolutely promise you, you will have a buffer equation on the exam. So I'll ask you to do one of these. The key to doing recognizing a buffer, and I've tried to emphasize on these, when you're working these types of problems, whether you're solving for a weak acid, a strong acid, a weak base, or weak base, the third thing in the pH mix is a buffer, or actually it would be the fifth thing. So if we look at the possibilities, we talked about how to do strong acids, weak acids. We talked about how to do strong bases, weak bases. If it's got a mixture of its weak acid and its conjugate base, or the weak base and the conjugate acid, that's a buffer pair. So the buffer is the other possibility of what we can calculate pH of. All right, so there's our table. We'll come back and use that on some of these other problems. Problem number 42 is a similar type of problem. On this one, it tells you wants to know what is the pH of the resulting solution. So if I think about this one, this is a weak acid on A, and this is its conjugate base, the sodium fluoride. Okay, so this is the conjugate base. So the two things together are going to react to form a buffer. Now, instead of just giving me the concentrations directly, it tells me it mixes these two solutions together. So you've got a certain volume and concentration of HF. You've got a certain volume and concentration of the sodium fluoride. So what we need to do with this is find out how many moles of each one of those species have, and then take into account the total volume. So we need to know what is the equation. The buffer equation will be based on what is the diluted concentration. So based on diluted amounts. It doesn't matter how much the initial amounts are, because you're going to dilute it some. But still, if it's a buffer, we need to know what is pKa. So pKa for the HF system, if we go back to our table and find hydrofluoric acid, HF, the pKa is 3.17. So we got that value. It's 3.17. Okay, so pH is going to be equal to 3.17, and then plus the log of the diluted concentration of the fluoride ion divided by the diluted concentration of the HF. Okay, so if we think about what would be the diluted concentration. So the way that we would find the diluted concentration is equal to, so I'm going to just write this out stepwise so everybody can follow along. It would equal to the moles of the fluoride divided by the total volume. And if I look at what is the diluted concentration of the HF, it's the moles of the HF divided by the total volume. Okay, so now it's the pKa, 3.17. The way that we find moles are equal to concentration times volume. So it's 150 milliliters times 0.25. So 150 milliliters times 0.25 molar. And then that would be divided by the total volume. And the total volume was 150 plus 225. So that's 375 milliliters. All right. So now if I look at the bottom half of it, Okay, that should have went on the bottom. So let me subtract that or take that out. So this was the acid form. And the protonated form, that's the HF, should have went down here. So didn't look close enough at the problem. So this is the HF. So the 150 milliliters times the 0.25 molar milliliters divided by 375 goes down on the bottom. On the top is the 225 milliliters times the 0.3 molar. Okay, so if I look and see what is common to these, you see that 375 on the top and the bottom, that's just going to cancel out. So the only thing that matters on the buffer is what is the mole ratio. Okay, so it doesn't really matter what this diluted concentration is. I just need to know what's the resulting mole ratio of these things. So when I take for the for the fluoride ion and multiply the 225 times the 0.3, that comes up to 67.5 millimoles. And if I do it on the bottom, if I've got the 150 milliliters times the 0.25, this one is 37.5 millimoles. Now, if you wanted to dilute or divide it out by 375 and get the molar concentration, you're going to come up with the same answer. I'm just showing you it's not necessary. All right, so if I take the 67.5 divided by 37.5, I find out that that ratio is 1.8. And if I take the log of 1.8, I find that that's a positive 0.26. And now I add that to the 3.17. And I find that the final pH of that buffer is 3.43. All right. So question on that one.
So like a problem like that, would the pKa be provided?
What do you mean divided?
Provided.
Provided, yes. Sorry. Yes, you have to do any buffer problem, you have to be given a pKa. Either that or you're given, I mean, if you think about the other side of it, I could give you a system where I give you the pH, I give you these concentrations and tell you that those concentrations result in this pH, and you would use it to find out what is pKa. I don't think I've ever given a test question like that, but maybe that's something new to try. But almost always we do it where the Ka is given. So that'd be something to be given to you. And either I would give it to you in the problem or I would attach the table of the weak acids. Okay. Anything else on it? All right. So this is the table of both the weak acids and weak bases. We'll refer back to it on the next problem. All right, so this is kind of like the problem that you just asked about, Aaron. It says calculate the ratio of if we look at what is this species, this is methylamine to the methyl ammonium chloride required to make a buffer of pH 10.24. So it's if we think about what is the methylamine, so let's just go highlight that guy. So this is methylamine. It's a weak base, and it ionizes and picks up a proton from water to make the methyl ammonium ion. And if I look at its Ka, so let me see if I can move you all over just a little bit. It's Kb in this one. Oops, it became black. The Kb in this is 4.4 times 10 to the minus fourth. All right, so the Kb is equal to 4.4 times 10 to the minus 4th. So here we know the pH. The pH is known, and we can calculate from this, we can derive what is the pKa. Okay, so we're going to figure out what is the pKa in this, but we can calculate that. But what it's wanting to know in the buffer equation is what is the ratio of these two things. So it's wanting to know what is the ratio of concentrations of the methylamine, that's the deprotonated form, so it would go on top, to that of the methyl ammonium. It would go on bottom. So we're actually on this one trying to figure out what is this ratio. And it doesn't matter what the absolute concentrations are, it's just what is the ratio of the two things. So if we're going to solve that, we would need to go through and first look at, figure out what is the pKa. So we know that Ka is equal to Kw divided by Kb. So Kw is 1 times 10 to the minus 14th. And we found the Kb from the table, 4.4 times 10 to the minus 4th. So this one's actually going to be a small, so something around 10 to the minus 10th. So the Ka is 2.3 times 10 to the minus 11th. So we've said that pKa is just the negative log of the Ka. So the Ka is 10.64. Okay. So now we know the pH. The pH is 10.24. The pKa is 10.64. So that's plus the log of the, and I'm just going to write the word ratio because that's what it asks for. This ratio, that represents this ratio of these concentrations. So I want to find out what that ratio is. So if I want to solve for that ratio, the first thing I've got to do is subtract this to both sides. So 10.24 minus 10.64 is equal to the log of the ratio. And if I subtract that, that's a minus 0.4 is equal to the log of the ratio. And if I've got something that's a log, I want to get rid of that. I take 10 to the x power of it, which is the anti-log. So I've got 0.4 negative. I take the anti-log of that, and that ratio becomes rounds to 0.40. It does. And the anti-log of the log is just simply equal to, on the other side of the equation, is equal to the ratio. So the ratio, when I have the ratio of 0.4 of methylamine to the ammonium chloride, that produces that pH of 10.64. So sometimes if we want to make something up of a buffer that's a certain pH, and we have a stock solution of a weak base and its conjugate acid in the system, we just need to know what ratio to put them together to yield that pH that we want. Now, if you've got a pH meter, you can adjust them until you get the pH that you want. You could just start with the weak base and add the acid to it to get the pH that you want. But if you don't have that, if we know the ratios to put together, we can calculate what it would be in a system. All right, problem 48 says 100 ml buffer solutions made with 0.175 molar HClO and 0.15 molar sodium ClO. It wants to know what is the initial pH of the buffer, and then what's the pH after adding some acid to it versus some base to it. Okay, so let's go back and look at what acid this is. This is chlorous acid. So, sorry, it's HClO. It's hypochlorous acid. Wrong one. So scratch that one. And hypochlorous acid has a pKa. Its Ka is 2.9 times 10 to the minus 8. The pKa is 7.54. So 7.54. So pKa is equal to 7.54. So the first portion of it asks, what is the pH of the system? So that is going to be pH is equal to the pKa, 7.54, plus the log of the deprotonated form. And the deprotonated form is the sodium salt, so that would go on top. And the protonated form is that of the acid that goes on the bottom. And we just take the log of that ratio. And the log of the ratio comes out to be a negative 0.07. We add that to the pKa, and the pKa is just a little lower, 7.47. Okay, so that's the initial pH. Now in part B, it wants to know what happens when we add 150 milligrams of HBr to it. Now HBr is a strong acid, and 150 milligrams, I mean, that's a little over 1/10 of a gram. That's quite a bit of strong acid in terms of mass. So there's 100 mils of this buffer. And if we think about what's going to happen, we would need to think about what's there initially and what's going to be the change that's going to occur. So if we add an acid to it, so what happens when we add this this acid in the system, get my pen back, is that the acid would react with the conjugate base, and it would react, and it would, the addition of this acid that we added, so we've added acid from the HBr, and it's going to react with this, and it's going to convert a portion of this back into some more of the acid form of the weak acid. So if I find out how much of these substances I have, and we set up an ice for it, we can calculate the final effect of adding the strong acid to it. So if I take concentration times volume for the acid, so it's 0.175 times 100 milliliters, that's 17.5 millimoles. So 17.5 millimoles of this weak acid. And if I do the same thing for the base, I've got 15 millimoles of this conjugate base. Now, if I look at the HBr, how much is in the HBr? So there's 150 milligrams. So that's 0.150 grams of HBr. And if I take and look at HBr, bromine weighs right at 80, so add 1 to it. It weighs 81 grams of HBr per 1 mole of HBr. And I'm doing everything in millis, 1 mole per 10 to the third millimoles of HBr. Okay, so I take the 150 times 1,000, or 0.15 times 1,000, and divide it by 81, and I find that that's 1.85 millimoles of HBr I'd added to the system. So when I add this 1.85 millimoles of HBr to the system, that's essentially adding H plus. What's going to happen is it's going to lose 1.85 millimoles of this, lose 1.85 millimoles of this guy, and it's going to form 1.85 millimoles of the chlorous acid. So now if I look at what I have at the end, I've got 17.5 plus the 1.85. So that's 19.35 millimoles. I've consumed all the acid now, and I had 15 of the conjugate base, but I lost 1.85 of it. So now I've got 13.15 left. So now I know the amount of the weak acid and the conjugate base. I just go back and plug this into the H&H equation. pH equals to the pKa, which is 7.54, plus the log of the deprotonated form goes on top, so 13.15 millimoles, divided by the form of the protonated, the 19.35 millimoles. So the ratio is 0.68. I take the log of that, and the log of this comes up to be a negative 0.17. And I see that the pH now is 7.37. So I started at pH 7.47, and I added this 1/10 of a gram of strong acid to it, and the pH only dropped 1/10 of a pH unit. That's what a buffer does, resist change to pH by the addition of a strong acid or strong base. So it had a minimal change by adding what would be a very significant change in pH. If I'd added that amount of acid to 100 mils of water, just by comparison, so if it had been 1.85, let me make my pen smaller. If it had been 1.85 millimoles of strong acid, H plus, added to 100 milliliters of water, okay, that would give us a hydrogen concentration of 0.0185. That would have yielded a pH of 1.73. So instead of dropping pH all the way down to 1, it drops it a total of 1/10. Okay. So anybody have a question about how that works? Now I'm just going to show you quickly how to set up if it were the part C of it. So if it were to happen with part C, it's adding a certain mass of sodium hydroxide, which is essentially a strong base, so it's adding OH minus. So what would happen with this one is that you would start with your ice again. You would start with the acid form. It would react with the OH minus, and it would simply form a little bit more of the conjugate base. So you would take and set up what is your initial amounts, and the initial amounts are the same. You would just have to figure out how many millimoles of OH minus are in this mass, and figure out what X would be here. And then this would be minus X, this would be plus X. So you would have 17.5 minus X millimoles and 15 plus X millimoles. So plus X millimoles. And then same way you plug it back into the H&H equation. So we can calculate what's the influence of a strong acid or a strong base on the pH of a problem. All right, let's take a look at the next one. So number 50 says calculate the pH of each solution. Calculate the initial and final pH after adding 1/10 of a mole of sodium hydroxide. Now this works just like the previous problem that I did. So I'm gonna just go through one of these for speed's sake. So first thing asks, what is the pH of 250 mils of pure water? Pure water is pH 7. You don't even have to do a calculation on that. So we know if it's pure water, the H plus equals the OH minus, and that only occurs at one point when pH is 7. All right, so we'll do B. So B says we have formic acid. So CH2OH is formic acid. So let me see where my table is. So yeah, formic acid, and formic acid has a pKa of 3.74. So for this particular one, pKa is equal to 3.74. Okay, you've got 250 mils of it, and the acid form is 0.195. The base form is 0.275. So initially, the pH would be pH is equal to pKa, and pKa is 3.74 plus the log of the concentration of the deprotonated goes on top. So the salt, that's the deprotonated, that would go on top. So the 0.275. And the protonated form would go on the bottom. The acid form, that would go on the bottom. So just take that ratio. And the ratio comes up to be 1.41. And then we take the log of that, and we take the log of that ratio, and it's a positive 0.15. So that adds up to 3.89. So the initial pH of this is 3.89. Now we're going to work it similar to what we did with the previous one, except this one's going to be the base. We're adding to it. So the weak acid, it would be the H, CHO2 plus the OH minus would yield the conjugate base, which would be the CHO2 minus. So if we set up the ice, if I go concentration times volume for the acid, so 250 times the 0.195, that tells me that this one has initially 48.75 millimoles. Now the amount of the OH minus that I'm adding is 0.01 moles, so that's equivalent to 10 millimoles. And I just like to use millimoles so I don't have so many spacing zeros. And if I do the same thing for the base, the 250 milliliters times the 0.275, this one is 68.75 millimoles. So the base is going to react with the acid. So less 10, plus 10. So this one's going to be down to 38.75. This is going to be consumed. This is going to increase to 78.75. So now we just go back to our H&H equation. pH is equal to 3.74 plus the log of the ratio. The base form goes on top. This thing's going crazy. Sorry. Base form goes on top. The acid form goes on bottom. So our acid form is the 38.75. So now when I take the ratio, the ratio is 2.03. I take the log of that, and I get a positive 0.71, and I add those together. It doesn't look right in my head, so I'm going to check my math again. 2.03, take the log of it. Yeah, I hit natural log instead of log. It's a positive 0.31, so plus the pKa, and the pH went up to 4.05. So it went from right at 3.9, it jumped about 1.5 pH units, or 0.15 pH units, to up to pH 4.05. So not a huge change in the system. All right, let's look at the next problem, problem 54. Problem 54 says determine whether or not each one of the following pairs would result in a buffer. Now, if we think about what we need to have a buffer needs to either be one, it could be a mixture of a weak acid plus its conjugate base, or two, it could be a weak base plus its conjugate acid. So either one of those pairs of system result in a buffer. And the other thing, we want them to be, we don't want to be more than 100 times of one form over the other. And ideally, we don't want it to be more than 10 times of one form over the other. So if we just, the key to working this type of a problem is a what is it? So if we look at HF, HF is a weak acid, and it's mixed with sodium fluoride. The sodium is a counter to a strong base, so the fluoride ion is a weak base. So in this case, a weak acid and its conjugate base, that results in a buffer. So that is a pair. Those two things are a weak acid conjugate base pair. Now the second one is a little different. So this is the mixture of HF, which is also a weak acid, but what it's pairing it with is HCl, and HCl is a strong acid. So the conjugate base is not present in this one, so this would not be a buffer. So B would not be. All right, so what happened if I mixed HF and KOH? Now HF is choose a different color here. HF is a weak acid, and KOH is a strong base. So you might initially think, well, this is not a weak acid conjugate base form, but what happens if I have HF plus OH minus is that it will react with some of the HF to make the fluoride ion and produce water. So it'll take a portion of this HF and convert it into the conjugate base. So this is the weak acid, and this becomes the conjugate base. The thing I need to look at what are the relative amounts of each one of these species. So if I look at how much HF I have, I've got 16.5 millimoles of HF. And if I look at how much of the KOH that I've got, the amount of strong base, this is approximately 7 millimoles. So in this case, when it reacted, I'd have somewhere in the neighborhood of 9 to 10 left of this one, and I would have formed approximately 7 millimoles of this guy. So that absolutely would make a good buffer. So this C is a buffer. Even though it doesn't look like it initially, it would. If it were to have had this number, if this would have been 250 milliliters, and this would have been the same 0.1, what would have happened was all of the HF would have been converted to the fluoride ion, and there'd be excess of this OH minus. So that essentially would just have been a strong base. That wouldn't have been appropriate. But in this case, it was. All right, D. On D, it is a mixture of a weak base, the methyl ammonium, and this is the methyl ammonium chloride. So this is its conjugate acid, and so that pair certainly is a buffer. And the last one is similar to what we talked about with the one on C. So this is the methylamine, and methylamine would react with, it's a weak base. It would react with a strong acid like HCl, which is a source of H+, and it would convert that into the methyl ammonium, which is the conjugate base or conjugate acid. So this is a weak base, and it would take a portion of that and convert it into the conjugate acid. So that would be the pair. So E would make a buffer as well. So the only one of these that that didn't make a buffer in the system was the weak acid, strong acid pairing in it. All right, any question on 54? All right, so 58, we only have a few more of these left. So 58 says, which buffer system would be the best choice to make a buffer that's pH at 9? So when we talked about buffers, the thing that we did to match the best buffer is we wanted to try to get the pH or pKa closest to the pH that we need. So we want to match the pH with the pKa. So pKa with our pH. So we want to look at each one of these systems and find out what is the pKa of each one of these guys. So the first one is hydrofluoric acid. So go to the table on the next page and find hydrofluoric acid. Its pKa is 3.17. So 3.17 is its pKa. Now that's a long ways from 9, so it's not A. The next one is nitrous acid, HNO2. And if I not find nitrous acid, its pKa is 3.34. It's not nitrous acid either. So that's a long ways from 9. Now, if I look at the next one on C, it's the ammonia and the ammonium chloride. So if I look at ammonia, I don't find ammonia under the acids because it is a base. So if I look at its Ka and versus its Kb, the Kb for it is 1.76 times 10 to the minus fifth. If I find the Ka, that's Kw divided by Kb. So 1 times 10 to the minus 14th divided by 1.76 times 10 to the minus fifth. So that is 5.68 times 10 to the minus 10th. So now I want to find out, take the negative log of that. So pKa is 9.24. Now that's getting pretty close to where we need to be. So 9.24. And then the last one is the chlorous acid. Let's see, hypochlorous acid. So hypochlorous acid, which is 7.45 on the wrong direction. So 7.45. It's definitely not A and B. If I look at the closer the better, ideally we said we wanted pH for a good buffer to be within plus or minus 1 of pKa. So that means that the one that's going to be fit within 1 would be the ammonium system, so 9.24. So it would be a good buffer from minus 1, which is 8.24, to plus 1, which is 10.24. And that falls, this 9 window falls in that. So it'd be choice C. So if you look at the old exam questions, I think I ask that almost every year, ask a question like that. So choose which one would be the appropriate buffer to yield something of this pH. So the other portions of it are calculate the mass ratios of each component. And we've already done problems like that, so that's nothing new. All right. All right. So 67 is one of the acid-base titrations. We need to do a problem or two like this. It says, consider the titration of 35 milliliters of 0.0 or 0.175 molar HBr. That's a strong acid, with 0.2 molar KOH, which is a strong base. So essentially, this is just going to be the reaction of H plus OH minus. And strong acid, strong base are going to react to form water. Okay, so it says to determine each. So what is the initial pH? So initially, the pH is just the concentration based on the strong acid. So it's the negative log of the concentration of the strong acid, which is 0.175 molar. So I just take that concentration, take the negative log of it. And the initial pH of this is 0.76. So that's the initial pH. So it's even less than 1. Okay, so B asks us to calculate what is the pH required or the volume required to reach the equivalence point. So the equivalence point is going to occur when the moles of acid, so the moles of strong acid, equal the moles of strong base. So the way that we find the moles of strong acid are the concentration times the volume for the strong acid would be equal to the concentration times the volume for the strong base. Now we know the concentration and the volume for the strong acid. So the concentration is 0.175 molar. The volume is 35 milliliters. We know the concentration of the strong base. It's 0.2 molar. What we're looking for is what is the volume of the strong base required to get there. So what we do, we just find that volume. So we divide both sides by 0.2 molar. That cancels that out. The molarity and the molarity would cancel out. So the volume of the strong base in milliliters is just going to be the result of multiplying and dividing. So the 0.175 times 35 milliliters divided by 0.2, and it takes 30.63 milliliters to reach the equivalence point. So at 30.63 milliliters, I would have consumed all of this H plus. It would be gone. There would be no excess OH minus, so it should be pH 7 at that point. Okay, so now we know that. So we know this is the volume that we need to reach the equivalent point in B. C says the pH when 10 mils of the base have been added. Okay, so if we think about this, we just simply set this up as an ice. So I've started with this this H plus. So this is step C. So I started with H plus. I'm adding OH minus, and I'm forming water as the product. All right, so if I take concentration times volume for the acid, so 35 milliliters times 0.175, I've got 6.125 millimoles of the H plus. The OH minus is 0.2, and it says at this point I've added 10 milliliters of it. So if I multiply the 10 milliliters times 0.2, that is 2 millimoles of the OH minus. So the two things are going to react. You're going to consume the one that's in the lowest amount, which is the OH minus. So -2, -2. It forms 2 millimoles of water, but water has no effect on the pH. So it doesn't have an influence on it. So minus the 2 would be 4.125. So now I still have excess H plus. What I need to find out is what is the concentration of the H plus at this point. So it's the 4.125 millimoles. divided by the total volume. I started with 35. I've added 10 to it. So now the volume is 45 milliliters. The millis and the millis cancel out. So 1.42 or 4.125 divided by 45 is equal to 0.0917. And if I take the negative log of that, find pH, I find that pH is equal to 1.03. So it's barely went up. It started at 0.76 and now it's went up to 1.03. Right? D says, what is the pH at the equivalence point? So at the equivalence point, I've taken all of the H plus, I've consumed it. There's none left. There's no excess OH minus. The only thing I've got is water. So pH at the equivalence point is pH 7. That's an easy one. Okay, so E, we'll do it quickly. E says, what is the pH after adding 5 mils beyond the equivalence point? So that would be the 30.63 plus 5 mils, which means that if this would be at 35.63 milliliters of the strong base added. So 35.63 milliliters added. Okay, so same starting conditions down here. So still the 6 1/8 millimoles. Now, if we look at how much OH I've added now, it would be the 36 or 35.63 times the 0.2, and it would be 7.126. It's probably supposed to be 5, but I got a rounding error. So I'm going to lose all of the H plus at this point. I'm going to lose that amount of the OH minus. I'm going to form that amount of water, but that's not going to influence anything. There's no excess H plus. If I subtract, I've got right at 1 millimole of excess OH minus, and I've got some water, but that doesn't control anything. So this is excess strong base. That means the concentration of the OH minus is the 1 millimole divided by the total volume. I started with 35 and now I've added 35.63 to it. So if I add those together, that's 70.63 milliliters. And I find the concentration of the OH minus is 0.1 or 0.0142 molar. So from that, POH is equal to the negative log of the OH minus, which is 0.0142. So POH is 1.85. And pH is equal to 14 minus POH. So POH is 12.15. So I expect the pH to go up, and it certainly does. So that's all the possible scenarios. So initially the pH is 0.76. It takes 30.63 milliliters to reach the equivalence point. When we've added 10 mils of base to it, the pH went up to 10 points or 1.03. It's neutral pH at the equivalence point, and when we went 5 mils beyond it, it's the 12.05. So just kind of remind you of what the shapes of titration curves look like for a plot of the volume of the NaOH, the titrant, versus pH. This is a 0 to 14 scale. It's going to start down real low, stay low, shoot up at the equivalence point, and then level out up here. So the equivalence point is this 7 in the middle. So this would be the at 30.63 milliliters. And if we look at our different points at 10 mils into it, that'd be somewhere around in here. It'd still be around this pH 1.03. And the final one would be somewhere up in here, 5 mils beyond it. So somewhere like in that. But just to help you visualize what's going on. Now, what would I give you in this problem? We spent a good while doing that problem, so it's not very realistic for you to see that as an exam question. However, any part of it would be an exam question. Okay, so I may ask you any part of that A through E. That's fair game to ask you something like that. But this covers every scenario: pre-equivalence, equivalence point, and post-equivalence. And that's all the possibilities. Once you can do that, you can do anything. Any questions on 67? Okay, I hope some of you are still awake out there. All right, so actually this is the same problem. I didn't think I would get it all on one page, so I copied it. So nothing new on this one. 86, I think we've got, just in terms of problems, just a couple more left. So we'll be off here pretty soon. 86 says write the balance equation and the KSP expression for each one of the following. So this is where you have a solid and you have to dissociate that solid into the cations and anions that make it up. So this would be the aqueous forms of those. KSP expression is products over reactants. All right, the products don't show up. So KSP is just the concentration of the calcium times the concentration of the carbonate. Now, if I look at the one for B, with the lead chloride, the thing we have to take into account on this one is that the dissociation is not 1-to-1. So lead dissociates into the lead 2+ plus 2 of the chloride 1-, and both of those are in the aqueous phase. So the KSP for this one is the concentration of the lead 2+ times the concentration of the chloride minus squared. So if let's see what my all right, so a couple of you have micro lab at 1 is what you wrote. So the only thing I'll tell you is that go back to the video. So I'm looking at the chats that have popped up. So if that's fine, don't worry about that. Just go back to the video and you can see what you would miss. On the silver chloride one, the silver or silver iodide, this one dissociates a 1-to-1. So it's going to be much like the one at the top. It's the silver cation aqueous plus the iodide aqueous. So the expression for KSP is just the concentration of the silver times the concentration of the iodide. All right, 88 says, given the values for KSP, calculate the molar solubilities for each. So we're just going to do the 2 that are here. So I don't know what A is asking for there. So it makes a hypothetical compound. So I've got this table 7.2 on the next page here. So let's do first this silver chromate. So silver chromate solid dissociates into the 2 silver cations plus the chromate anion, which is a divalent, so 2-. So if we look at the dissociation that occurs, if this is solubility, this would be 2 times solubility because this is a 1:2 ratio, and this would be solubility. So if I'm going to write the KSP expression for that, it would be the concentration of the silver squared times the concentration of the chromate ion. Now I'm just going to simply plug in the values for S for the silver and the for the chromate. And for the silver, it's 2S, so it would be 2S squared times S. So 2S squared is 4S squared, and then times S, so KSP equals 4S cubed. So now if I want to solve for the solubility, it's KSP divided by 4S. So I'd take the 4 and divide it by both sides. That would give me S cubed, and get rid of that cube, because I'd have to take the cube root of both sides. So the solubility is the cube root of KSP divided by 4. So this is a 2-to-1 ratio salt. So that's where that we can't get these values in the table for how to set that up. So we just need to go find the silver chromate. And I find silver and silver chromate. It's 1.12 times 10 to the minus third. So 1.12 times 10 to the minus third divided by 4. And then I've got to take the cube root. And when I take the cube root of it, I get .0. Did I write a value down right? Nope, I didn't. 1.12 times 10 to the minus 12th. I don't know where I was going with that. Let's try that again. 1.12 times 10 to the minus 12 divided by 4. Now I'll take the cube root of it. That's more realistic. I get 6.5 times 10 to the minus 5th. 6.5 times 10 to the minus 5th molar. So that's the solubility for the silver chromate. Just quickly set up the one for the calcium hydroxide. Calcium hydroxide dissociates in the same ratio. It's a 1:2. And in the similar way that we just worked the previous one, when it's a 1:2 ratio, the solubility is simply going to be the cube root of KSP divided by 4. So we just need to go look up the value for KSP. And for calcium hydroxide, 6.8 or 4.68 times 10 to the minus 6th. 4.68 times 10 to the minus 6th divided by 4, and take the cube root. And again, play along with these in your calculator. Make sure you and your calculator are friends. 1.05 times 10 to the minus 2 molar would be the solubility for C. All right, anybody have a question on 88? Anybody that's left? There's only 4 of you left, so the rest either didn't show up or have checked out.
How are you punching the cube root in your calculator?
Okay, so that's a good question. So my calculator has a y to the x key, something to a power, and then the second function on it is the it's the xth root of y. So on mine, I would put in so my order of operations is I would hit 4.68 times 10 to the minus 6 and I would take and divide it by 4 and hit the equals. And then whatever the answer was to that, I would hit the X to the Y button, and then hit the second function. And then that would take the X root of it, and I would put 3 in, and then equals. Did that get you there?
Almost. I wasn't typing as fast as you were talking, but I can watch this part of the video again.
Okay. But the key thing is the second function to this takes it to the version that you need, which is the X root of it. And to do solubilities, you've got to be able to use setup calculators. All right, let's see if there's anything left. Okay, that's it. So that's a good overview of the problems that you have to do on the mastering chemistry. Does anybody have a mastering chemistry question you want to ask? You can also ask some tomorrow. That assignment's due tomorrow night. But does anybody have anything going forward here?
On the test, I noticed you said it was open Thursday and Friday. So as long as we take it before midnight Friday, is that correct?
I'll set the test up that way. That's
Or where was the deadline on?
Say again.
Okay.
The deadline will be midnight.
Oh, you said. Okay.
So I'll set it up where it opens Thursday at midnight. So it's going to open at 12 o'clock a.m. on Thursday, and you'll have 48 hours to work it in there. So they'll probably be at a 2.5 hour time limit. So that's the thing you have to think about. You have to do it continuously. So you've got to lay out 1 2.5 hour block of time where you feel mentally fresh and nobody's going to bug you. You think you're going to have good internet service. Again, if something happens and you get locked out for some reason, the only way we can do it is I have to restart the test for you. So I have to clear your previous attempt. So if you get a message that says you've been disconnected, the test is going to be set up so you can't start it again yourself. You have to send me an email and I have to reset it, but I'll constantly be checking email during that period of time. So it may be maybe 20 or 30 minutes at the most before it would before I would know it, but typically it's going to be quicker than that. Right.
Okay. And then we have to start at question 1 and work all the way through. We can't skip around.
Well, the questions are presented in random order. That way 2 people can't be working the test together. So your question 1 won't be the next person's question 1. But you can't skip around.
Okay, gotcha.
I put it where you can't go backwards. You can only advance through the.
Okay.
So, and the sole reason I do that is to try to prevent cheating online as much as possible.
No, that's fine. I was just wondering.
Yeah. Okay. Anything else? All right. So we used most of our time this session. Try to work through some of the problems, look at the old tests, and I'll log on tomorrow at 11:30 during our normal time. And whatever mastering chemistry or old test questions y'all want to do, I can pull any of them up, put them on the screen, and we can work through them. So I'll spend as much time as y'all want to spend on that tomorrow. Okay. That signing off. See you tomorrow.
See you.